In this chapter, we have learned a variety of integration techniques. Let's review a little bit about all of them. The first section was primarily a review of basic integration techniques from Calculus 1. In this integral, we'll do a u substitution for the denominator. So let u equal x plus 10, and then du will equal dx. And because we have a definite integral, we're going to change our bounds. If x is equal to 0, u is equal to 10. And if x is equal to 5, u is equal to 15. Now the only thing we haven't replaced is this x in the numerator. So look at your substitution and solve for x. X would equal u minus 10. So this is the same thing as the integral from 10 to 15. U minus 10 divided by u du, or dividing both terms by u, we have 1 minus 10 over u du. Now anti-differentiate, the antiderivative of 1 is just u, minus 10 natural log absolute value u, evaluated from 10 to 15. So that will be 15 minus 10 ln of 15 minus 10 minus 10 ln of 10, or 5 minus 10 ln 15 plus 10 ln 10. So that's totally fine. Also, you could combine those two logs like this. Factor out a 10, write it as ln 10 minus ln of 15. And that will be the log of 10 over 15. 10 over 15 is 2/3. This is the same thing as 5 plus 10 ln 2/3. Next, sine root x over root x. The only thing that is probably worth trying here is letting u equal root x, which is the same thing as x to the 1/2. So there, du is 1/2 x to the negative 1/2 dx, or 2 du is equal to 1 over root x dx. So now we have twice the integral of sine of u du, which is the antiderivative of sine is negative cosine plus c, or negative 2 cosine root x plus c. In section 8.2, we learned the technique integration by parts. The formula for that is that the integral of u dv is equal to uv minus the integral of v du. And usually you let u equal the part in the integral that kind of goes away if you take derivatives repeatedly. In example A, we'll let u equal x, and dv will equal cosine of 2x dx. Now if u is x, du is just dx. And to find a v, we have to anti-differentiate cosine of 2x, and that will be 1/2 sine 2x. So that tells us that the integral of x cosine 2x is equal to uv, so 1/2 x sine of 2x, minus the integral of v du, so minus 1/2 the integral of sine 2x dx. So that will be 1/2 x sine 2x minus 1/2 times, now the antiderivative of sine 2x is cosine 2x with the coefficient of negative 1/2 plus c. So we have 1/2 x sine of 2x plus 1/4 cosine of 2x plus c. Next, let's find the integral of x to the 3/2 times ln x. So here, probably best to let u equal ln x. it isn't very easy to anti-differentiate ln, so we're going to have dv equal x to the 3/2 dx. So if u is ln x, du is 1 over x dx. And if dv is x to the 3/2, v is x to the 5/2 times 2/5. So our integral is equal to uv, so 2/5 x to the 5/2 ln x minus v du, so minus 2/5 the integral 1 over x times x to the 5/2 dx. Now in this integrand, you can write that as x to 1 power by subtracting the exponents. So we have 2/5 x to the 5/2 ln x minus 2/5 times the integral of x to the 3/2 dx. So 2/5 x to the 5/2 times ln x minus 2/5 times x to the 5/2 with another coefficient of 2/5 plus c. So your final answer is 2/5 x to the 5/2 ln x minus 4/25 x to the 5/2 plus c. Right, the integral of arctan 3x. So we're going to let u equal arctan 3x. And then what's left, dv, will just equal dx, in which case v is equal to the antiderivative of 1, which is just x. And du is 1 over 1 plus 3x squared, so 9x squared, times 3 dx. So arctan 3x integrated is equal to x arctan 3x minus 3 times the integral of x over 1 plus 9x squared dx. And now we'll do a substitution for the 1 plus 9x squared, and let's just use a different variable like w. w equals 1 plus 9x squared. dw is 18x dx, and I just have x dx, so we'll say 1/18 dw. So we have x arc tan of 3x minus 3 over 18 integral 1 over w dw. So x arctan 3x minus 1/6 ln absolute value of w, but w is 1 plus 9x squared, so no need for the absolute value bars, plus c. And the final kind of application of integration by parts are these around the world problems. So here, let's start by letting u equal e to the 2x and letting dv equal sine x. Then v will equal negative cosine x, and du will equal 2e to the 2x dx. So the integral of e to the 2x sine x dx is equal to uv, so negative e to the 2x cosine x minus v du, so because v is negative, actually can become plus 2 e to the 2x cosine x dx. And then we're going to do it again. And this time we'll pick u and v in the same sort of manner, like letting dv equal the trig function and u equaling the e to the x function. So now we'll let u equal e to the 2x. So du is equal to 2 e to the 2x dx. dv is equal to cosine x dx. And v is equal to just plain old sine x. So we now have that the integral of e to the 2x sine x dx is equal to negative e to the 2x cosine x plus 2 times uv, so e to the 2x sine x minus twice the integral, so minus v du, and that 2 comes out, minus 2e to the 2x sine x dx. And let's distribute that 2. So you have negative e to the 2x cosine x plus 2e to the 2x sine x minus 4 integrals of e to the 2x sine x dx. And now you're back where you started. So I'm going to take this expression and add it to both sides. So remember that what this is all equal to is a singular e to the 2x sine x dx. So when I add 4 of them to that, I have 5 times the integral e to the 2x sine x dx is equal to negative e to the 2x cosine x plus 2e to the 2x sine x. And to find the integral of e to the 2x sine x dx, you just divide by 5. So the integral of e to the 2x sine x dx is equal to 1/5 times negative e to the 2x cosine of x plus 2e to the 2x sine x plus c. The next technique we learned were how to evaluate trigonometric integrals. So this is just a combination of trig substitution and some common trigonometric identities. So here I have sine cubed of theta times cosine cubed of theta. So I'm going to have it as my end goal to let u equal sine of theta. And then du is equal to cosine theta d theta. Theoretically, this integral can be worked out either way. You could let u equal cosine of theta, but it's easier this way because sine's derivative is positive cosine, whereas cosine's derivative is negative sine, and it's easy to get the negative signs, like as in the negatives mixed up. So if I'm going to let u equal sine x, I have to only have one cosine left over. So make this cosine squared, or cosine cubed, into cosine squared and cosine. So I have sine cubed theta cosine squared theta times a singular cosine theta d theta. So this cosine theta d theta is saved to be the du. Now these cosine squared thetas, you know that sine squared plus cosine squared is equal to 1. So cosine squared theta is 1 minus sine squared. So I have the integral from 0 to pi over 2 sine cubed theta 1 minus sine squared theta times cosine of theta d theta. And when I make my u substitutions, I get u to the third 1 minus u squared du. And you also have to change your bounds to being u values. So if u is sine theta, sine of 0 is 0. And if u is pi halves, sine of pi halves is 1. And now I just find this antiderivative, or this area under this curve. So I have the integral from 0 to 1, u cubed minus u to the 5th du. So that will be 1/4 u to the 4th minus 1/6 u to the 6th, evaluated from 0 to 1. So we have 1/4 minus 1/6. So that will be 3 over 12 minus 2 over 12, or 1/12. Next, if the power on your sine or cosine is only even, you're going to have to use the double half-angle identities to figure this out. So sine to the 4th of 5x is equal to sine squared of 5x, quantity squared. And sine squared theta is equal to 1/2 1 minus cosine of 2 theta. In this case, my theta is 5x. So this is equal to the integral of 1/2 times 1 minus cosine 10x at quantity squared dx. And now we still have that squared outside, so we're going to expand. So first off, that 1/2 squared makes 1/4. So we have 1/4 times the integral of 1 minus 2 cosines of 10x plus cosine squared 10x. We have to change this cosine squared into being just regular cosine. So we use the fact that cosine squared theta is 1/2 1 plus cosine 2 theta. So that will give us 1/4 times the integral of 1 minus 2 cosine 10x plus 1/2 times 1 plus cosine twice 10x is going to be 20x dx. So we have 1/4 integral of 3/2. That comes from adding this 1 to that 1/2 once it's distributed. Minus 2 cosine 10x plus 1/2 cosine of 20x dx. Now go ahead and antidifferentiate. I have 1/4, 3/2 x. Now an antiderivative of cosine is going to be sine, so minus 2/10 or 1/5. 1/5 sine of 10x plus 1/40 sine of 20x plus c. We also use identities with secant and tangent and cosecant and cotangent. So first of all, with this one, tangent to the 5th, secant to the cubed, secant cubed. So here, we're going to have to let u equal secant of theta. And if we do so, du is secant theta, tan theta, d theta. So I need to save a secant and a tangent to be the du, and I need to change all the rest of the tangents into secants. So this becomes the integral of tan to the 4th theta, secant squared theta, times secant theta tan theta d theta. And then tangent to the 4th theta is tangent squared squared, and tangent squared is secant squared theta minus 1. And now we can make our u substitution, and we have the integral of u squared minus 1, the quantity squared, times u squared times du. And expand u squared minus 1, we have u to the 4th minus 2u squared plus 1 multiplied by u squared. Distribute that u squared and we get u to the 6th minus 2u to the 4th plus u squared du. And now antidifferentiate. I'm going to plug u back in the same step. So I'll have 1/7 secant to the 7th of theta plus 2/5 secant to the 5th theta plus 1/3 secant cubed theta plus c. Next we have tangent squared secant to the 4th theta. So if you're going to let u equal tangent, you have to save a secant squared and turn the rest of the secants into tangents, and you can do that here because the power on secant is even. So let's let u equal tangent of theta. And then du will equal secant squared theta d theta. So this integral is the same thing as tangent squared theta times secant squared theta times secant squared theta d theta. And that last part's going to be saved for your du. So we have tangent squared theta. Now secant squared is tangent squared theta plus 1 times secant squared theta d theta. Or this is the integral of u squared times u squared plus 1 du, which is u to the 4th plus u squared du. So anti-differentiate and plug back in u, we'll have 1/5 tangent to the 5th theta plus 1/3 tangent to the 3rd theta plus c. Now the next thing we learned was how to do trigonometric substitutions. So we use these techniques to evaluate integrals that involve radicals of the form a squared minus x squared plus a squared, and x squared minus a squared. For integrals of the first type, we let x equal a sine theta. For the second type, we let x equal a tan theta. And for the last one, we let x equal a secant of theta. So for this first example, we have the integral of x squared over 4 minus x squared to the 3/2 power. It doesn't look like there's a root, but there actually is, because this could be written as x squared over the square root of 4 minus x squared cubed dx. So that's of our first form, and we're going to let x equal 2 sine of theta, in which case dx is equal to 2 cosine theta d theta. So let's input everything. So first of all, we have x squared, that will be 4 sine squared theta, times dx, which is 2 cosine of theta, d theta, divided by the root of 4 minus 4 sine squared theta, all cubed. So that's 8 sine squared theta cosine theta d theta over, now in the denominator, 4 minus sine squared theta is actually equal to 2 times cosine of theta. Remember that because the 4 can factor out, giving you 4 times 1 minus sine squared theta, and then 1 minus sine squared is equal to cosine squared. And you have all that rooted, so that's your little thought bubble. Alright, and when I cube that, I'm going to get 8, so the 8's will cancel. And I really have sine squared theta cosine theta over cosine cubed theta. And one of those cosines will cancel, giving us the integral of sine squared theta over cosine squared theta, which is the same thing as the integral of tangent squared theta. And you don't have a formula for tangent squared, but you can change it into secant squareds using your trig identities. Tangent squared theta is the same thing as secant squared theta minus 1, and that will antidifferentiate into tan theta minus theta plus c. And now we're going to go back to original substitution to change our thetas back into x's. So first of all, notice that x over 2 is equal to sine theta. So construct your triangle. Here's my angle theta. Sine is equal to the opposite over the hypotenuse. So my adjacent side is equal to 4 minus x squared. It's just the Pythagorean theorem. So tan theta, tangent is the opposite over adjacent, so that will be x over the root 4 minus x squared minus theta. Now theta, to find that, you'd have to apply arc sine to this, so theta will be arc sine of x over 2, so minus arc sine, or inverse sine, that is, x over 2 plus c. Alright, next we have a definite integral, and since we have x squared minus a number, we're going to make the substitution x equals secant of theta. And if x is equal to secant, then dx is equal to secant theta, tan theta. And we have to also change our bounds. So first of all, we know that 1 is equal to secant of theta. And since secant is 1 over cosine, this occurs when theta is equal to 0. And 2 equals secant theta is the same thing as saying 1/2 equals cosine theta. And that happens at the angle theta equals pi thirds. So this becomes the integral from 0 to pi thirds root secant squared theta minus 1 multiplied by secant theta tan theta d theta divided by secant of theta. So those secants cancel, and then you should remember that secant squared theta minus 1 is tangent squared, and then when I square root that I just get plain old tangent, so I have tangent of theta times tan theta d theta. So the integral from 0 to pi thirds tan squared theta d theta. And just as before, tangent squared theta is equal to secant squared theta minus 1. We anti-differentiate secant squared theta, we end up with tan theta minus theta, evaluated from 0 to pi thirds. Alright, so we'll have tangent pi thirds minus pi thirds. Tangent of 0 is 0, and so plugging in 0 yields 0. Now tangent of pi thirds is sine pi thirds over cosine pi thirds, so root 3 over 2 divided by 1/2. And root 3 over 2 divided by 1/2 will just be root 3, so our final answer is root 3 minus pi over 3. The next technique we learned was integration by parts. So here we use partial fractions. So one way to test that you know how to decompose things is to give you some partial fractions and just have you give the decomposition and not actually do any integrals. So these all look awfully similar, but that squared in the bottom keeps moving and there are different plus signs and minus signs. So for part A, first of all, notice that you have x squared plus 4 over x times x plus 2, x minus 2. And the decomposition there will be a over x plus b over x plus 2 plus c over x minus 2. The order of the b, c, and a is not very important, but the point is you should have 3 different fractions that are added together with denominators of x, x plus 2, and x minus 2. Now this second one has a repeated linear factor. The x squared is repeated. So when you would try to decompose this, you must have a term a over x, another one b over x squared, and one more that's c over x minus 4. For part C, this x squared plus 4 is an irreducible quadratic factor. So when decomposing that, the partial fraction decomposition is a over x plus bx plus c over x squared plus 4. Remember that when you have an irreducible quadratic factor, the numerator has to be a linear factor. So bx plus c is how you represent that. That's a linear term. Let's actually use the partial fractions technique to integrate this. So 1 over y squared minus 4y minus 12. So first of all, that denominator is going to factor into y minus 6 times y plus 2. And that will equal a over y minus 6 plus b over y plus 2. Now if you multiply both sides by y minus 6 and y plus 2, we end up with 1 equals a times y plus 2 plus b times y minus 6. And then getting common terms together, we'll have y times a plus b, and then plus 2a minus 6b. And because there is no y on the left-hand side, a plus b must equal 0, and 2a minus 6b has to equal 1. So then a is equal to negative b, so negative 2b minus 6b is equal to 1, negative 8b equals 1, b is equal to negative 1/8, and then a is equal to the opposite of that, or positive 1/8. And so now the original integral you had is the same thing as the integral of 1/8 over y minus 6 plus negative 1/8 over y plus 2. And integrating each part individually, we'll have 1/8 ln absolute value y minus 6 minus 1/8 ln absolute value y plus 2 plus c. The integration part is often not very difficult with these. The hardest part is breaking them up. So in this example, we have two irreducible quadratic factors. So finding the partial fraction decomposition is going to be a little bit tricky. So 3x cubed minus x squared plus 6x minus 4 over x squared plus 1 times x squared plus 2 will equal ax plus b over x squared plus 1 plus cx plus d over x squared plus 2. Now multiply by the denominator and we get 3x cubed minus x squared plus 6x minus 4 equals ax plus b times x squared plus 2 plus cx plus d times x squared plus 1. And distributing all that out, we end up with ax to the third plus bx squared plus 2ax plus 2b plus, that's just the first one, plus cx to the third plus dx squared plus cx plus d. And now let's group all the terms. So first the x cubes. I have this one and that one. So we'll have x cubed times a plus c. And now the squareds, we have this one and this one. So plus x squared times b plus d. And then for the x's, I have this 2ax and this cx. So we'll have plus x times 2a plus c. And lastly, for the constants, we have 2b plus d. So, based on, now we have that 3 will equal a plus c, negative 1 will equal b plus d, and 6 will equal 2a plus c, and negative 4 equals 2b plus d. Now we can use this equation and this one together to find the values of a and c. So c will equal 3 minus a, and plug that in to the other equation. We have 6 equals 2a plus 3 minus a. So I think we then get that 3 is equal to a. And once you know that, you can figure out that c is equal to 0. Using this equation, we have that d is equal to negative 1 minus b. Plugging that into here, we have negative 4 equals 2b minus 1 minus b. So negative 3 equals b. And then using that, d will equal 2. now that we've found the values of a, b, c, and d, our original integral is equal to the integral of 3x minus 3 over x squared plus 1 plus 0x plus 2 over x squared plus 2. And there's no trick here, 0x really is just 0. So what I have, I'm going to write this into a couple integrals. I will have 3 times the integral of x over x squared plus 1 dx minus 3 times the integral of 1 over x squared plus 1 dx plus 2 times the integral 1 over x squared plus 2 dx. Now this first integral can be solved if you make a u substitution for x squared plus 1. You can work out the details for that yourself, but what you're going to get is 3 over 2 ln of x squared plus 1, and the absolute value bars aren't necessary there because x squared plus 1 is positive. The second integral is actually arctan. And the final one, you have this formula for the integral of 1 over x squared plus a squared, and that's 1 over a arctan x over a. And in this case, the a is actually root 2. So you have plus 2 over root 2 arctan x over root 2 plus c. So that will be 3/2 ln x squared plus 1 minus 3 arctan x. Now 2 over root 2, if you rationalize, you actually just get root 2 arctan x over root 2 plus c. Alright, the next section we had concerned how to find limits using L'Hopital's rule, and this lets us find limits of the form 0 over 0, infinity over infinity, 0 to the power of 0, all sorts of different types of things. So first of all, 0, this one, when you plug in 0, tangent of 0 is 0, we'll get ln of 1, which is also 0, so we can apply L'Hopital's rule, so this limit is equal to the limit as x goes to 0. Tangent's derivative is secant squared, so if secant squared of pi x times pi over the derivative of ln of 1 plus x is 1 over 1 plus x. And now you can plug in 0. Secant of 0 is 1, so we'll have 1 times pi over 1. So this limit's equal to pi. The limit as x goes to 0 plus of x squared ln x. This is of the form 0 times infinity, so we can remedy that by changing it into the limit as x goes to 0 plus ln x divided by 1 over x squared. And remember that 1 over x squared is the same thing as x to the negative 2. So I have ln x over x to the negative second. And as x goes to 0, ln of x goes to minus infinity, 1 over x squared goes to infinity, so this is an infinity over infinity indeterminate form. So you apply L'Hopital's rule, and we get the limit as x goes to 0 plus of 1 over x over negative 2x to the negative 3. So that's the same thing as the limit as x goes to 0 plus of 1 over x divided by negative 2 over x cubed, which if you simplify becomes 1 over x multiplied by x cubed over negative 2. And that will, when we cancel an x, give us the limit as x goes to 0 plus of x squared over negative 2. And now we can actually input 0, and this limit is equal to 0. Alright, let's find the limit as x goes to pi halves plus of tangent of x to the power of cosine x. It probably won't get this complicated on your test, but it's a good illustration of how limits like this work. So if you plug in 0, tangent of pi halves goes to infinity at that point. Cosine of pi halves is 1. So we have infinity to the first. Who knows what that's equal to? So we start by letting y equal tan x to the cosine x power. And then take the natural log of both sides. And ln of y will equal cosine of x times ln of tan x. And we'll find the limit as x goes to pi halves plus of this expression. And the first thing to notice is that it's not in the right form. So I'm going to change this into ln of tan x divided by 1 over cosine x, or cosine x to the negative first. And now we have an infinity over infinity kind of limits. Is that right? Right, now we apply L'Hopital's rule, and we get the limit as x goes to pi halves from the right. The derivative of ln of tan x is 1 over tan x times secant squared x. And the derivative of 1 over cosine x is negative 1 cosine of x to the negative second times sine x. So simplifying slightly, we have the limit as x goes to pi over 2 plus secant squared x over tan x. Now in this denominator I have negative sine over cosine squared, which will then reciprocate into cosine squared x over negative sine x. And actually, those negatives cancel, giving us a positive. Because that was negative sine x and that negative 1. There we go. So now, remember that secant squared really is 1 over cosine squared. So what I have here is the limit as x goes to pi over 2 from the right. Secant squared times cosine squared is going to give us 1. Tangent is sine over cosine, so I'll have 1 over sine squared x over cosine x, which is the same thing as the limit x goes to pi over 2 from the right, cosine x over sine squared x. And at pi halves, cosine is 0, sine is 1, so we'll have 0 over 1 or 0. And what that tells me is that the limit as x goes to pi over 2 from the right of ln of y is equal to 0. So move the limit inside of the ln of your limit, x goes to pi over 2y is equal to 0. Now use e, the limit as x goes to pi over 2 from the right of y is equal to e to the 0 or 1. And the final topic in this unit was evaluating improper integrals. So those are integrals with an infinite discontinuity, or actually any discontinuity, or a limit that is infinity. So for this first example, we will change that infinity to a b and take a limit as b goes to infinity. And this is 2x plus 1 to the negative third. So now if we anti-differentiate 2x plus 1 to the negative third, we're going to have a 1/2. 2x plus 1 to the negative second divided by negative 2, evaluated from 1 to b. So we'll have negative 1 over 4 times 2b plus 1 squared plus 1 over 4 times 2 plus 1 squared. So this first term, because b gets large, that first term goes to 0. And I end up with 1 over 4 times 9, or 1/36. with this integral, the problem point is 0, so we're going to change this into the limit as b goes to 0 from the right, integral from b to 1. And next I'll divide both terms by root x. So x over root x is just root x, or x to the 1/2, minus x to the negative 1/2 dx. So the limit as b goes to 0 plus. Now let's antidifferentiate. The antiderivative of x to the negative 1/2 is x to the 3/2 times 2/3, minus x to the negative 1/2 will be x to the 1/2 times 2, evaluated from b to 1. So the limit as b goes to 0 plus 2/3 minus 2, that's plugging in 1, take away 2/3 b to the 3/2 minus 2 square roots of b. And now as b goes to 0, both of those second terms go to 0, so all we have is 2/3 minus 2, which is negative 4/3.